What we are going to study now is the so-called common ion effect. The common ion effect is when you have in problems, you have to find the solubility of a specific solid, but in that solution there is already one of the ions. Let me give you an example. If in your beaker you have a solid and that solid contains hydroxide, well, if this solution is water at pH 7, well, your concentration already in that water at pH 7, the concentration of hydroxide is 10 to the negative 7. Notice that these hydroxides did not come from the solid, they come just from water. Water being neutral water, it already has 10 to the negative 7 molar of hydroxide. So how can we calculate the solubility when there is already one common ion between the solution and the solid? Well, in this case, your initial amount of hydroxides is indicated here as 10 to the negative 7. We assume neutral water. So what is the change? Well, the solid will dissolve to a certain extent. And notice that for each mole of solid dissolving, there will be 1 mole of iron and there will be 2 moles of hydroxide. Therefore, in equilibrium, what changes now is that sure, there were 0 moles, that this iron was not common with the solution. So in equilibrium, we have X number of moles of iron, and you have now 2X plus what there was already in solution in there. Okay, so notice that now if we plug this in, my KSP, concentration of iron is X, concentration of hydroxide is 2X plus 10 to the negative 7, and we have to square this concentration, and this is equal to my KSP. What you have here is a cubic, right? This will be an X squared times X. It's an X to the third. We will not ask you to solve analytically these equations, but you can plug it into tools such as Wolfram Alpha or any other website that solves polynomial equations for you. So you will see that in this case the X, there's only one real value for X, the other one are imaginary, so this is 10 to the negative 5 molar. Does solubility change if this initial concentration changes? Yes. So in this case, the solubility of iron hydroxide will be conditional to the pH, if you will, of the solution or of water in which this iron hydroxide will be dissolving. Typically, sometimes you will see that the solubility can be given in grams per liter. So in here, the solubility that we calculated was in molarity. That's what you always plug in into the KSP. So this is moles over liter. Okay, can we convert that into grams per liter? Well, we just need to convert moles into grams. 1 mole, if you calculate the molar mass of iron hydroxide, is around 90 grams per mole. Okay, and if you multiply this, what I get is 1.13 times 10 to the negative 3 grams per liter. Okay, so you may even see that there is 1.13 milligrams per liter. Alright, so just so you know how to convert the X in molarity into grams per liter, you just convert moles into grams or vice versa. A qualitative question that you may find in terms of common ion effect is if the solubility, that is the value of X, will change if we decrease or increase the pH. Well, let's see. If you increase the pH, notice that what you're doing is increasing the OH negative. Okay, if you increase the concentration of OH negative, you can apply, you don't need to solve the cubic equation again. You can apply just the Le Chatelier principle. You are adding products to the reaction, so the reaction will, by Le Chatelier, it will displace Le Chatelier, it will displace to the left. In other words, there will be less solid that will dissolve, so the solubility will decrease. Okay. Likewise, if your pH is smaller, that is, you're increasing the concentration of hydronium, you are decreasing the concentration of hydroxides. Again, by Le Chatelier, you are decreasing the amount of products by Le Chatelier, the equilibrium will displace to the right. In other words, there will be more solid dissolving. Your solubility will increase. Hopefully you can discuss these kind of problems both qualitatively and quantitatively. Both are important, so we'll keep practicing.